Good day! This is Ricardo Punzalan, and for this video, we're going to investigate, model, and solve a problem from item number 13 of Chapter 1, Problem Set B of our module in Math Investigations. This presentation will make use of the discussed previous 4 steps in problem solving. This video will also discuss the basic concepts of modular arithmetic that will be the tool to be used to find a solution. Now, without further ado, let's proceed with the problem. The integers greater than 1 are arranged as shown in this slide. The questions are, which columns do 100, 1000, 1999, and 99,997 fall in this arrangement? Now, as I've said earlier, we're going to employ Polya's 4 steps to solve this problem. The first step is to understand the problem. We need to know what our aim or goal is. We want to find what columns these numbers belong. But before that, we must first identify the pattern that goes with the given arrangement. As we look closely, we know that the sequence starts with 2 and goes on consecutively. We also do notice that there are 4 columns per row, and if you really observe the pattern, we see that odd rows go from left to right and even rows go from right to left. For the second step, we're going to devise a plan. This plan will be a little bit lengthy, but I'm sure it will be worth it in the end. I'm going to make some changes with the arrangement to see a more obvious pattern. I'm going to subtract 1 from each entry in the arrangement. And this is the result. We can now observe that the first 4 natural numbers are on the first row, the next 4 on the second row, and so on. Now if you ask, how is this different from the original pattern? I'm going to answer you with this. We have a couple of ways to tell time. The first one, the common one, is that we count 12 hours from midnight until noon, and another 12 hours from noon back to midnight. The first one we call AM, and no, it's not at morning or almusal or anything else we may be thinking of. It stands for Ante Meridiem. Ante meaning before, and Meridiem meaning noon. Same goes with PM, which stands for post meridiem, and we know why we call it that way. There is another method to tell time in which we also begin counting from midnight, which is 00 or 0 o'clock, but for 24 straight hours until the next midnight, which resets at another 0 o'clock. If we're going to tell 3 p.m. in this format, we will be adding 3 hours from the 12 noon and we end up with 15 o'clock. 7 p.m. would be 12 plus 7 or 19 o'clock, and so on. Now, what if we know the 24-hour time scheme and we want to revert back to the AM or PM equivalent? How do we know what time 1730 is? There's an easy way, and a more complex yet useful way. The easy way is to obviously subtract 12 from the given 24-hour time if it exceeds 12 o'clock. 1730 minus 12 equals 530. If it exceeds 12 o'clock, it's way past noon, and therefore the time is 5:30 p.m. There is a more complex way. Imagine living in a planet with 36 hours per day. If we want to use our standard 12-hour clocks in this planet, how do we know where the hour hand points at when 27 hours has elapsed from midnight? You can do another subtraction of 12 if you want to, but a better way is to divide 27 by 12. But you may ask, why? 27 is not divisible by 12. Do we get fractions as a new time scheme in this planet? Not actually. If you remember the basic division algorithm from elementary, there are 2 things that we'll focus on: the quotient and the remainder. 27 divided by 12 is 2 with the remainder 3. This implies that 2 clock cycles have occurred, and if there existed AM, PM, and QM in this planet, we now know that we are in a QM phase. The remainder, which is 3, refers to the number where the hour hand points at such instance. This is the very basic concept of modular arithmetic. In modular arithmetic, we have 2 basic operations, div and mod. 27 div 12 refers to the whole number quotient of 27 and 12, which is 2, as mentioned earlier. 27 mod 12, on the other hand, pertains to the remainder when 27 is divided by 12, which is 3. Now that we understand the foundations of modular arithmetic, let's head back to the arrangement I've modified earlier. You can now view this pattern as a 4-hour clock that goes on and on. This would be how it looks like. If we look closely again, we see that all numbers on the first and fifth columns appear to point at 0 on the clock. This means that numbers in the first and fifth columns are congruent to 0 mod 4. In other words, dividing these numbers by 4 yields a 0 remainder. Another thing we can observe is that numbers in the second, third, and fourth columns somehow follow the numbers 1, 2, and 3 on the clock, going left to right on the odd rows and right to left on even rows. Without looking at numbers on the edges, let's investigate each row. Row 1 is 0 div 4, meaning when we divide numbers 1, 2, and 3 by 4, we get 0 as a whole number quotient. Then the first entry, 1, has a remainder of 1 and is on column 2. The second entry, 2, has a remainder of 2 and is on column 3. The third entry, 3, has a remainder of 3 and is on column 4. However, when we investigate the second row, 5 has a remainder of 1 and is on column 4. 6 has a remainder of 2 and is on column 3. 7 has a remainder of 3 and is on column 2. Together, these three numbers are congruent to 1 div 4, which means when we divide each by 4, we get 1 as a whole number quotient and their respective remainders. So we can also conclude for these numbers in columns 2 to 4 that when we divide the number by 4 and results in an even whole number, the sequence moves the value remainder from left to right, starting from column 2 inclusive. If the result of division is an odd whole number, the sequence moves from right to left, starting from column 4 inclusive. Now what about the numbers in the edges? If there is no remainder, the number is either on column 1 or column 5. We can also use the div operation to know which of the two will be the number's position in the arrangement. If the quotient is odd, the number is in column 5, as with 4 and 12. And if the quotient is even, the number is in column 1, as with 8 and 16. Combining these sets of observations, we can design a flowchart to model the pattern and identify a given number's position. Let the number you want to locate be x. First stage, does the number yield a remainder of 0 when divided by 4? Or in other words, is the number divisible by 4? If yes, then your options are narrowed down to column 1 and column 5. If we divide the number by 4, is it odd or even? If it is even, the number is in column 1. Otherwise, it is in column 5. If for the first question we have a different answer, that is, there is a remainder when divided by 4, we go to the other side, find the value of that remainder. Then we will identify if the number belongs to a row that goes from left to right or right to left. If the whole number quotient when the number is divided by 4 is even, we count the value of remainder starting from column 2 to the right, inclusive. If it is odd, we count the value of remainder starting from column 4 to the left, inclusive. Let's try a number that we see in the arrangement to check if this flowchart works properly. Try 13. If we divide it by 4, we have a remainder of 1, so we go on this side of the chart. The numbers in either columns 2 to 4. The whole number quotient when we divide by 4 is 3. Following the flowchart, we could count one column from column 4 inclusive, which means number 13 is in column 4. Let's check if it's correct. Yes, it is. Now we know the algorithm works properly. It's time to proceed to step 3, which is to carry out the plan. But before we find the value of 100, 1000, and the rest of the numbers as in the problem, we should subtract 1 from each of these numbers first. Remember that I've modified the arrangement by also subtracting 1 from each entry. If we'll try 100, we would have to subtract 1 from it, and we get 99. This 99 would be the x value where we implement the algorithm we've created. Is 99 divisible by 4? No, we have a quotient of 24 and a remainder of 3. The quotient is even, so we count 3 columns from column 2 to the right with the final answer of column 4. How about 1000? We subtract 1 to get 999. 999 divided by 4 is 249 with the remainder 3. We count 3 columns from column 4, because it is odd, to get the final answer of column 2. For 1999, we subtract 1 to get 1998. Divide it by 4 to get 499, which is odd, with remainder 2. We count 2 columns from column 4 to get the final answer of column 3. Lastly, for 99,197, we subtract 1 to get 99,196. This one is divisible by 4 with a quotient of 24,999. Hence, it's either in column 1 or 5. An odd quotient predicts that 99,197 is in column 5. Without having to continue writing the pattern, we have predicted where each number would go. Though it was a bit tedious that we had to understand an underlying concept in order to obtain a solution, it is indeed worth it, because we can predict a number's position no matter how high it can be. We have discovered the essence of modular arithmetic to solve problems like these. Now I will give a similar problem for you to answer. You may pause the video to ponder about the solution to this problem. The numbers from 6 onwards are arranged as shown. Find which rows to 57, 120, and 1001 belong. Here comes the most important part of Polya's 4-step process of problem solving. We will attempt our solution, or in our case, the application of modular arithmetic in similar problems. Now this problem I've constructed here has many similarities to the original problem, but there are a few key differences. Number 1. The numbers go top to bottom, then bottom to top, instead of the original left to right, right to left. The number sequence begins with 6 instead of 2, and each column now has 6 entries instead of the 4 entries from the original problem. My approach to solving this problem is to make the sequence start from 1 instead. So in order to see the pattern and apply the modular arithmetic we've done earlier, we will subtract 5 from each entry, and now we see the clear pattern. Now we have a hint that instead of modulo of 4, we're going to use the modulo of 6 in this case. Let's observe 1, 2, 3, 4, and 5. These numbers have the same value as the remainder when divided by 6. They're in the respective row numbers as well. For 7, 8, 9, 10, and 11, we'd be counting 1, 2, 3, 4, and 5 rows upwards from row 6 inclusive. That is, if the remainder is 1, it's in row 6. If remainder is 3, it's in row 4, and so on. Numbers 1 to 5 have even whole number quotients, which is 0, and numbers 7 to 11 have odd number quotients, which is 1. So we can deduce the condition that if the quotient is even, the sequence is downward. If it is odd, it's upward. For the multiples of 6, we can observe that odd multiples are on row 6, while even numbers are on row 1. I think we have the sufficient data to create a new flowchart which will serve as an algorithm in determining which row a certain number is located. Let x be the given number minus 5. Is it divisible by 6? If yes, let's determine if the quotient is odd or even. If it is odd, it's in row 6. If it is even, it's in row 1. Meanwhile, if it is not divisible by 6, let's identify the quotient and remainder. If the quotient is even, count the value of the remainder from 1 or row 1 downwards inclusive. If it is odd, count the value of the remainder from row 6 upwards inclusive. Let's test a value if it works flawlessly. Try 23. Is it divisible by 6? No. So we identify its quotient, which is 3, and remainder, which is 5. The quotient is odd, so we count 5 rows from row 6 upwards inclusive. We end up with the final answer of row 2. And based on the pattern here, that prediction is correct. Now this tool is ready to be tested on the original pattern. For 57, we subtract 5 to obtain a value of 52. We divide it by 6 to obtain a quotient of 8 with a remainder of 4. It is not divisible by 6, and the quotient is even, so we count 4 rows downward to get the answer, row 4. For 120, we subtract 5 again to obtain 115. We divide by 6, and we know it's not divisible by 6, to obtain a quotient of 19 and remainder of 1. The quotient is odd, so we count 1 row upwards from row 6 inclusive to get row 6. And finally, for 1001, we subtract 5 again to obtain 996. It is divisible by 6, and the quotient would be 166, an even number. Therefore, we know that 1001 is in row 1. There we have it. We have solved the problem. By being able to solve this as well, we can be assured that modular arithmetic will work with sequences like this in some way. To summarize, we learned how to solve problems like these. We learned about Polya's 4 steps which help us develop an effective tool in solving the problem. We also touched the basics of modular arithmetic, which turned out to be the key in finding a solution. That's all for this presentation. Thank you for watching.